Okay, guys, welcome to AP Chemistry. This is your first content lecture. I'm hoping that you logged on to Google Classroom successfully, or you wouldn't actually be at this lecture, and that you did do the tutorials on how to use Google Classroom, how to submit things in Google Classroom, and some of just the general housekeeping of our classroom. Okay, we're going to be winging it, guys, and what I mean by winging it is that we're on uncharted territory. I'm not used to doing a hybrid class. You're not used to being in this hybrid class. So we're going to do the best we can do. I'm sure there will be hiccups and issues, and the best thing that you could do is whenever something like that happens, you let me know. You send me an email, you communicate to me, and tell me, hey, I have this problem, it's not working right. You can sometimes send me messages via the Google Classroom in the assignment. You can do a personal comment. If you have something that you think is a discussion for the class, you can put it in the stream, right? So just be aware of that. We're going to get into our first set of notes. What I'm going to start off trying to do, and if it works, we'll continue doing it, is that I'm going to have you guys take the notes at home. And so when you're in the school, we will practice and we will work on things. If you are working remotely during our classroom, you will be working at home on the similar types of worksheets, problems. If you're following along on a lab, you would be following along through Zoom. I really don't know how all this is, and it is August right now for me when I'm making this video, so that could change by the time we're in class about a month from now. Alrighty, so we're going to start off with chemistry. You're taking AP Chem, but even if you're taking regular Chem, you have to start with some of the basics. Your challenge this year, because you chose to do AP Chem, is that you will have 2 years of content in one. So when sometimes I say to you, I'm going to push you, it's because we have to cover the content, right? So we're going to go on the premise that everything is set, that we will be taking Regents in June, and we're going to plan for that. So I'm going to start off with the first note packet you got in class. And if you didn't get it yet, and I asked you to watch this video, it's fine. You watch the video, and then you get caught up in class. So we're going to talk about chemistry. You're here to study chemistry. So chemistry is a very broad definition, and the definition is that, oops, sorry guys, I'm just testing out my little marker here. So that's the other thing is I've got these controls on the bottom of the screen that I'm not used to, so I have to figure out how well it'll work and all that kind of thing. So all new stuff and updates and things like that. So we're going to study chemistry. And the broad definition of studying chemistry is that it is the study of matter. And all matter. We're made up of matter. Everything around us is made up of matter. Yes, there is the ethereal antimatter. You hear it in movies and stuff, science fiction things. There is a antimatter, and that's for you to study in physics. If you take AP Physics, it's one of the things that is done after the AP exam. Okay, so we're going to look at what's tangible to us and in some ways intangible because we can't see it. So when we study chemistry, we look at matter. And matter is just defined as anything that has mass and takes up volume. That's what matter is defined as. Okay, but everything has matter. So when we partake in learning chemistry, and for that matter, any science, you are going to have to make observations. Okay, so even if we don't get to do too many hands-on labs before the AP, and don't fret it, I'm trying to be optimistic. At some point I feel things will iron out with the COVID and we'll be back in person all the time, at which point that is when we'll do a lot of labs, okay? So when we do labs together right now, I've been told I have to do most of the demoing it unless I can really work out you guys being safely in the lab, right? But you still have to make observations. Observations are really important. So a lot of the laws and theories that we're going to start out with is in this intro, matter and atoms and all that kind of thing. We're all done by just our 5 senses. Right? So there are two different ways to use our senses. One is to do something that's qualitative. So when we talk about things that are qualitative, we are looking at things that have a quality in it. Okay, so look at the English that's there. The word quality is a description. And there's certain things you have to be careful of in terms of description, but it is a descriptive nature. Okay, that's what a quality is. Then we can have things that are numbers or quantity, right? So you change those to y's at the end, and you have quantity, which means a number. And those are two types of observations we're going to make. We're going to go back and forth between using our observations to make conclusions and then furthering that conclusion in our scientific method. And we're going to make more observations, and then we'll come to new conclusions. So it's sort of a circular type of journey we go on. And again, you've been through scientific method training in a lot of your science courses. You probably did it at the very beginning of the year like we're doing now, and you're kind of like, okay, that's all well and good. Let's just get on to the fun stuff. But you're going to find that when you're in an AP course, scientific method really plays a big role in your learning process. So we will look at conclusions. Conclusions are based on your observations, and they're usually a general statement. There are what's called deductive reasoning and inductive reasoning. So we will use both. And you really have to assess what you see and what you experience. Sometimes those experiences are odors, they're sounds. There's a lot of different things. Okay, now, don't cheat on this, right? Don't cheat. I'm going to give you this box. You're going to read it. And then when you're done, you're going to count as you read. And you're only reading it once, so you can read it as slowly as you want. You're going to count how many F's there are. And what I mean by don't cheat is, you can watch this video and then you can like fast forward to the answer, and then you can come back and go, oh yeah, I got the right answer. It's just observe. Go ahead and read. Sorry for the phone ringing. Okay, so having said this, if you're not done reading, hit pause, read it, count your F's. Okay, so now, come on. I just went on to the next slide. I want you to think, how many F's did you count? And the point of this is, write it down, side piece of paper, wherever you want to write it. The point of having you count your number of F's is that all of us bring to the table our own experiences and our own things that have shaped how we observe what goes on in the room, in our life. So some of us will have one set of numbers. Some of us will have two different sets of numbers. We'll have different numbers based on our own experiences. So I'm going to go back through this and I'm going to say, okay, what's there? Whoops. All right. Back on highlighter. So here's one F, two F's. Most people get those because of this beginning of a word, but here you come to of. So it's three F's. Oh, here's another of, four F's. Scientific in the middle of the word, so sometimes people skip that. Study combined with the experience of many years. Okay, now some of you might say, I think experience is spelled wrong. It is. So some of you might have caught that. Right? So here's the thing. Most people get these two really easily. A lot of people do see this, but the ones that people miss are in the preposition, because our brains are trained that a preposition really doesn't mean much. Why has my pen stopped working? Interesting. Okay, so keep in mind that even small things can slip our vision, and we have to be paying attention. Brings us to the scientific method. Okay, normally I have you try to figure out a puzzle on a scientific method, and we'll see if we can do this in class. All our scientific method that we do in our room is based on our five senses. We don't really have the high-tech equipment to get below what I called more in depth than our five senses. We use our five senses to make an educated guess. We observe what goes on around us and we make a guess. Then we devise experiments to test our guess. So this is the circular part right here. Okay, I get an experiment, I get data. I evaluate it, I go back and I look to say, do I have to revise my guess? Okay, now maybe I do, maybe I don't. It depends on my data. If this data validates my guess, then I come up with a theory. Okay, that's the conclusion. And in scientific method, you continue to test this. Okay? And again, we do this round and round thing. And why this is not writing, I don't know. And once you have this continually tested, and the difference between here to here, the scientific theory to the scientific law, is that the law is a general consensus. There isn't any contradictory data to it. Okay, there isn't any argument about it. You've tested and tested and tested and tested and tested, and it comes out always the same. So then when you have a group of experts get together, they say, look, it's always coming out the same, we can come up with a law. When you test and you analyze data, that you usually make plots. Okay, so when you make plots, you have two different variables. You have your independent and your dependent. Right? So in this situation with the independent and the dependent, you have to know for chemistry, the independent is always the X and the dependent is always the Y, always. And when you name a graph, the label will always be Y-axis versus X. And I don't know why my pen's not writing on the slide. It's like there's a delay. Okay. So if it is volume versus temperature, then the volume would be on the y-axis because it's always y is always stated first. Temperature is always the x-axis is always stated second. Right. So again, we make observations, we design experiments, and if all of these experiments are justifying your hypothesis over and over and over and over again, then it becomes a scientific law when it's devised as being, by many scientists, valid. So now we get on to state of matter. We are going to study states of matter repeatedly in this course. We will not talk about plasma. So those of you who are really into science and say, oh, but there's another state and it's plasma, we don't talk about plasma in here. You gotta wait for physics. Okay, so we have a solid. There are key words in this. A solid is something that has definite shape, definite volume. Some of the key words here are that it has a regular geometric pattern. That is something to look for as a description. It is crystalline, and it has the strongest forces of attraction. When you see this as drawn anywhere, it is neatly stacked, like over here in the corner, one on top of each other. So if you were to draw a solid, you would always have them really close, maybe just slightly separated, and it's really hard for me to draw on this. And then as you can see, my little pointer draws and then it doesn't. Why did it erase? Okay, and you stack them nice and neat and close together. And that's considered a regular geometric pattern. A liquid have molecules that are farther apart. They can slide past each other. There's more movement. It is not rigid. And here's things that are important. It has a definite volume. Right? So if I had a graduated cylinder and I had 50 mLs in it, and then I had a squat beaker and I had 50 mLs in it, and then I threw it on my lab bench and it spread out, that would still be 50 mLs. But the big thing is it has no definite shape. The shape that it'll adhere to has to do with its intermolecular forces and whether or not it is in a container with sides. So this will have a high shape to it because of the narrowness of the graduated cylinder. This will be contained and have a shape more like a pie shape because it's going to be in a squat beaker, and this would just be spread out on the table. Okay, and when we draw them, notice how they're a little farther apart. Gas is the farthest apart. So you know how these are all very far apart here. This one, they're spread out. When you draw a gas, the easiest way to do it is put one in each corner of the box, because they'll give you a box to draw it in, and one in the middle, and that is a gas. Okay, if I were to draw a solid using a box, it would be all located closely packed together in the bottom of the container. If I were to do a liquid, or try to recognize a liquid, it might be more towards the bottom, but spread out a little like that. I'll put a fifth one in there. It usually asks you to do 4 or 5. A gas spreads it out completely. Gases will fill the container completely. Okay. No definite shape, no definite volume, weakest attraction. They are compressible. I'll try to do a little demo in class about compressibility. If I forget, remind me. Okay, so that's your 3 states of matter. Now, we're going to do exercise about classifying matter. Matter contains of either a pure substance or a mixture of substances. Okay, so if it is considered just a substance, if I say it's a substance, it is one substance, it is only a substance, then it is considered pure. Nothing else is there. Right? So if I had a handful of sodium chloride, it would be a pure substance of just sodium chloride. If I had a glass of distilled water and I looked only at the water and it had to be distilled, then it would only have water and it be a pure substance. It has to be distilled though. Okay, water out of the tap is not a pure substance. It's a mixture. So a pure substance contains one element or one compound. Only one thing. Because it's only one thing, we say its composition is homogeneous or homogeneous. Okay, either way. You can say it either way. So this being the same throughout. This word right here. Same throughout. One thing, that's all we have. Okay. Now, we can have a mixture, which is the other type of classification of matter. And a mixture then contains 2 or more. So more than one in a pile. So if I had a mixture of sand and salt, that's a mixture. Oil and vinegar is a mixture. Oil and water is also kind of a mixture. It ends up being what's called an emulsion, and so does this, but it's not one thing throughout. Okay, a pizza. especially pepperoni, is a mixture. There's more than one thing there. Okay, if we look at particle diagrams, okay, particle diagram means you have a diagram with circles and squares in it that represent atoms and elements and molecules. So I could have an element that is monatomic. I could have a diatomic molecule. I could have a compound. Okay, that is a mixture. There's more than one thing there. And what they'll do is they'll throw a couple more of these in here. Okay, but over here, if it's a pure substance, I would have all the same thing in the box. Right, that's bad drawing, but it's all the same thing. Monatomic element in the box. In this case, it's a gas because it's spread way out. These are pure. This is a mixture. Okay, so a substance can be one of two things. This is pure. When I say it is a substance, it is pure. It can come off the periodic table if it is an element. Okay, it can come off the periodic table if it's an element. It would have only one type of atom present. Its smallest form right now, because we're not going to talk about splitting an atom apart right now, we say that the smallest form of matter is an element. And the element, well, I shouldn't say, excuse me, not an element, it's an atom. The atom makes up elements. So right now we're saying this. And you can't break it down any more than that. Right? So if they say you have a substance that cannot be broken down, you have to think element. It cannot be broken down. Right? So if you see those words, cannot be broken down, you think element. Okay. We can have things that are called monatomic elements, like a metal sodium or single carbon, or we can have diatomic elements. And you have to remember these. There are 7 of them, right? So the 7, and you will see them listed out, is iodine, that's I2, bromine, chlorine, fluorine, I should probably write them over here, iodine, oops, sorry guys, I keep hitting the buttons on my stylus, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. Okay, I bring clay from our new home. Iodine, oops, bromine, chlorine, Cl, fluorine is just the F, oxygen, nitrogen, hydrogen. Right, there's another way I'll show you in class on how to memorize this. It has to do with the periodic table. Element number 7 is nitrogen. There's 7 of them. If you look at the periodic table, you have nitrogen, oxygen, fluorine, chlorine, bromine, iodine, makes a number 7. And all way up in the corner, you have hydrogen. Okay, so these guys like this, like a Tetris piece, and then hydrogen by itself. Okay, so you have to memorize those. You need to know them. Okay, a compound is also a pure substance, but it can be made up of 2 or more elements that are combined, and you will see them touching in diagrams. These 2 touch here, so that means there's a bond. These 2 touch here, there's a bond. And actually for this particular one, because that's water and sodium chloride, this actually goes into what's called a lattice structure. It's not just this sitting alone. You have chlorine here and a sodium here, and there's forces of attraction. Okay, so Particle diagrams, again, touching means there's a bond. Same thing here. These are diatomic, but they have a attraction between the two atoms. They don't like to live alone. They need a partner. That's a diatomic. Over here, there's a difference between this and this. This is a compound because there's two different ones. This is just a diatomic molecule. This is a molecule and a pure element. And we could separate this. They don't like to exist that way. Its simplest form is still an atom, but on diatomics, they exist as molecules. Kind of confusing, but you'll get it straight in a little bit. All right, so these compounds will have new properties. They won't be the same as the properties that the elements had. They might be a combination. Their smallest form is a molecule, but here's the kicker. It can be broken down, and this is really important. This can be broken into its elements, but it has to be chemically done. You have to do something like electrolysis, hit it with energy. You might have to hit it with high heat to break the bonds apart, but chemically you have to do something to it. Okay, now, the cool thing about chemistry, let's look at sodium chloride. Right? Sodium is a very reactive metal. It explodes when you put it into water. Right? You get an explosion. It doesn't explode. You actually cause gas to be released that explodes. Chlorine is a gas. It'll kill you if you inhale it. But when you put them together, hopefully some of you realize you get table salt. So we take two dangerous elements that exist by themselves, we put them together, and we have a compound we use to season our food. All right, let's talk about the different types of mixtures, and then we're going to talk about separating the mixtures. All right, so the first type of mixture is a homogeneous mixture. Homo meaning the same, or uniform. So this will be uniform throughout. You cannot tell any difference between the material as you slice through the material. So that's why it says you can't tell a difference. It's if you slice through the material, it's the same. There's no differentiation of it. It is completely uniform. Right now, having said that, all solutions which are designated by AQ, and AQ means aqueous. This is a U, aqueous. Right, those, that designation, anything, NaCl with an AQ. CaCl2, designated AQ. Because of how salts get dissolved by water, they are considered, and again, aqueous is dissolved in water, they are considered homogeneous. These will always be, by default, homogeneous. Okay. Now, on the other side, we have what's called a heterogeneous mixture, non-uniform. If I take slices, I can either have distinct phases or I can have regions that are different. So your slice will be different from slice to slice. You essentially might have layers in there. Okay, so a heterogeneous mixture is something that can be a bunch of different things. I like to use pepperoni pizza. All right, unless you have an excessively anal retentive pizza preparer, right? If you look at a slice of pepperoni pizza, this slice might have only 3 pepperonis on it, and then another slice might be, and this is how my slice would be, slathered pepperoni. Right? So depending on how you cut it, depends on how many pepperonis you get, or when you bite into it, how many pepperonis do you bite into? So this would be a heterogeneous mixture. Okay, when you look at particle diagrams, and you're like, what do you mean particle diagrams? Particle diagrams are little boxes with little symbols in it that represent what's going on a particle level. All right, so I'm going to erase some of my, hey, ink over here. Back to my pen. If I cut this and take cuts of it, right, if I get down to here, I have a little bit of this atom and a little bit of this molecule. This is layered. This whole thing going this way is layered. I have a place where I switch from an element to a compound. They separated or they just exist that way. That's layered. On this one, and this is a bad drawing, okay, because the reason why I say this is a bad drawing, this is supposed to represent AQ, where these are supposed to be assumed to be evenly distributed throughout the box. Okay, a lot of times now how they will represent AQ is they'll have one of the pieces of a salt, and then it'll be surrounded by water molecules. And you'll be like, oh, that's water surrounding a molecule, so it's a solution. And then they'll have the other one also surrounded by a water molecule, but a different way. Okay, and when you see that, you're like, oh, there's water hanging out there, and it's around the two different types of atoms. Okay, last slide for today, separating mixtures, or last slide for this lecture, separating mixtures. There are many different ways to separate mixtures. They will ask you most commonly, well, about actually all of these, but filtration. You must understand that filtration separates things that are large versus small, but what we really talk about is a solid versus an aqueous. Okay, the aqueous will go through the filter, the solid stays on top of the filter, right? It will not, if you have something dissolved, right, because aqueous means you have ions in solution, it's not going to separate the ions out of the water. They will go through with the water because they're attracted to the water. If you have sand and salt, for instance, if you dissolve this, the salt will become AQ, goes through the filter. The sand stays on top. Whenever they talk about what can be separated via filtration, you look for anything that is solid in AQ as a mixture. Okay, that's really important. Evaporation, right? That's when you want to boil off the water to get the solid back. So anything that is AQ, you take away the water and you will get the pure substance. And they'll say, how do you get back the substance once you dissolve it in water? You evaporate it. Right? I'm going to go over to distillation. You can also distill it if you want to collect the water back. Right? Now, distillation will heat a mixture, and then the material will boil off based on its boiling point. You can separate liquids. This is usually used to separate liquids. You can also get salt back out of water and get both your salt and your water. They have to have different boiling points. Okay, distillation is used in petroleum industry. It's how we purify out the different things like octane versus kerosene versus like petroleum jelly. Right, that all comes from distillation. And you have this apparatus where it has this little heating neck, and then it has what's called a fractionating column that comes up. It has these little plates in them. I know it doesn't look like it does, but it does. And then you have this cooling column that comes down, and then it deposits in a collection vessel. On this cooling, you have a water jacket that wraps around here to cool the vapors. And up at the top, you usually have a thermometer to read the temp, and it's stopped up there. So the little vapors come up this, they travel up here, If they're at the right temperature, they then reach here and they come back down here and they drip into this and collect. And that's distillation. Okay, you can physically separate it out, and that means take a magnet, like if you had iron or paper clips or something magnetic in a pile and you only wanted that stuff, you could take it out with a magnet. You could use what's called a sieve, which means it has different size holes. So say it's not magnetic, but the things are different size rocks. You could get the small rocks to fall through and the big rocks to stay on top. That's a sieve. Okay, so it's physical separation. Chromatography is physical separation that's based on two things. Yes, it does it by size, but it also does it by what's called how it's solvent, how it works with the solvent. Its solubility. You probably have done chromatography. You should have done it in living environment with the chlorophyll pigments on the paper. Right? So this is solubility versus size. If it is soluble in what's called the running solvent, it'll dissolve and it'll go faster. If it doesn't like the running solvent, it'll sit at the bottom of the paper for a long time. Right? So that's how you separate things. And that is the first lecture.